All right, we had some questions for homework on page 592. The questions were question 2, 5 to 8, and 10 to 16. Any issues for those of you who did the questions with 2, 5 to 8, and 10 to 16? Today? 11, 15, 16? Any others? 8? 8, 11, 15, 16. Going once? Yep. 14, 7. Going once, going twice. Good. All right. Number 7. What would happen to a magnet if you broke it into 2 pieces? Well, we know the domains point in a certain direction, right? Which way do domains point? From south to north. The magnetic field outside of the magnet points from north to south, but inside of the magnetic field, and therefore the domains point from south to north. Now, if you cut that in half, if you split it in 2, the domains still point in a particular direction, and they therefore still point from south to north. They have to have a place where they're coming from and a place where they're going to. So in the end, if you broke it in 2, you'd end up with 2 magnets, each one with a south pole and a north pole. Doesn't change anything. Okay, we're not going to have a south magnet and a north magnet. We know that we can't have a single pole. Okay, we have to have 2 poles in each one. Next question, question number 8. A negatively charged sphere is approaching you. Describe the magnetic field surrounding the sphere and its direction. What would happen if the sphere were positively charged? So let's picture this now. This negative sphere is coming towards you. It's like an electron coming out of the board here. If it's coming out of the board, we're going to use the Wiregrass Rule, right? Thumb in the direction of the particle, which is out towards you. Fingers in the direction of the field, which way is the field? Clockwise. The magnetic field is clockwise for number 8. Number 11. Using the domain theory, explain the following observations. A magnet attracts an unmagnetized ferromagnetic material. Well, here's my magnet. It's got the domains aligned. Here's my non-magnet, but my ferromagnetic material with the domains pointing in seemingly random directions here. How does it magnetize that? How does it attract it, I should say? Kind of just gave away the answer. How does it attract the unmagnetized ferromagnetic blue material? It starts to line the domains up. Yeah, it temporarily aligns the domains in this blue one. So for a short period of time, as long as it's nearby, those domains start pointing in the same direction. Stroking a nail with a magnet magnetizes the nail. It's essentially the same thing, right? You bring another magnet nearby this nail, then it's going to cause the domains in the nail to start pointing in the same direction. As long as you stroke it in the same direction. Okay, if you do it like, if you stroke it in one direction and then go backwards and then sideways and whatever, then you're just going to scramble the domains as much as they were before. So that's not going to help. As long as you stroke it in one direction, you should magnetize it. And finally, the metal table leg affects a compass. Why does a metal table leg affect compass? Yep. Good, because the table leg is a ferromagnetic material, right? And it's going to, ferromagnetic materials attract magnets, and what's a compass? It's a magnet, right? Next question was number 14. Why is it difficult to get, here's a good question. Sound familiar? Why is it difficult to get an accurate bearing with a magnetic compass near the poles? Yep. Yeah, field lines are either going into the Earth or out of the Earth, right? Here's the magnetic North Pole. Here's the magnetic South Pole. And the field lines are kind of pointing downwards or upwards at that point. And you can't get, with a traditional compass, at least a normal compass, can't point up or down. It's got to point horizontal, parallel to the Earth. (15) Do magnetic field lines always run parallel to the surface of the Earth? Explain your answer. Let's go back to that diagram that was in question number 13. These field lines aren't exactly parallel to the Earth, but they're pretty much parallel to the Earth, right? Are all field lines parallel to the Earth in all places on the Earth? No. Where are they not parallel to the Earth? at the North Pole and the South Pole. And that's why we can't use a traditional compass there, right? Because the compass points parallel to the Earth, or on the plane of the Earth. But at the North Pole and the South Pole, the field lines point into the Earth or away from the Earth, so therefore the compass can't react to that. And question 16, here's a good one. If a current-carrying loop is bent into a loop, or current-carrying wire, I should say, is bent into a loop, why is the magnetic field stronger inside the loop than outside? Good question. Jai, you think you get an answer for that? Okay.
Because if the outside the loop, it would be the same as it was just in a straight line. But on the inside of the loop here, the magnets like this, the ones on the left side are pointing towards the right, but the ones on the right side are also have to be pointing towards the right, as it's just going to compound the magnetic field.
Yeah. It basically, it is. Now, I'm not sure if that explanation made perfect sense to everybody, but you're right. As soon as you said that word compound, that's when it kind of rung home that, okay, you know exactly what you're talking about there. When you've got a coil of wire, we use the coil rule in order to find the direction of the magnetic field, right? But we could use the Wiregrass rule. Okay, each loop of wire has a magnetic field that it produces. Let's take a look at one of those loops of wire. Okay, let's take a look at one of those loops of wire kind of from the end, all right? Let's say the electric current is going this way. Okay, this is not a magnetic field. This is an electric current. Got it? Okay, now let's look at the direction of the magnetic field. Okay, if we stick our left fingers in the direction of that current, which is counterclockwise there, then the magnetic field inside would be pointing into the page, right? Now, if we looked at it right up here, then we would still find that the magnetic field at that point was pointing into the page, okay, inside the coil. Okay, same thing at the bottom. The magnetic field is pointing into the page. Same thing over here. The magnetic field is pointing into the page. So wherever you do it, wherever you do the hand rule on that one particular loop of wire, you're going to find the magnetic field points into the page inside the coil. Now, all of those magnetic fields add together. The magnetic field that was caused by the current right here, the magnetic field that was caused by the current here, and caused by the current here, and caused by the current here, they all add together to give me a really strong magnetic field, because you've got, essentially, as you go around it, an infinite number of magnetic fields generated inside that coil. Now, you have the same thing outside, right? Magnetic fields are generated outside as well. But the magnetic field caused by the current right here outside would be pointing out of the page. The magnetic field caused by this one outside would also be out of the page. The magnetic field caused by this one would also be out of the page, and the magnetic field caused by this one would also be out of the page there. These don't add up. These don't add up to give me a stronger magnetic field because they're in different places. So the magnetic field inside the coil caused by this current right here at this one spot adds up with this one and this one and this one to give me a strong magnetic field. Compounds, okay, as you said, Josiah. Okay, the magnetic field caused outside of the loop, right here, still points out of the page, does right here, does right here, does right here as well, but they're not adding up because the magnetic field outside are in different places. Does that make sense? No? Let me try that again then. Makes sense to Josiah, who gave me the answer in the first place. Not charges, magnetic fields. Magnetic fields. Okay, let's see if we can do a little manipulative here. Okay, here's my loop. Go ahead, Dane.
Would it be possible to make another wire through the center? Would it make the magnetic charge of that wire even greater to start straight to the center of the loop in that wire?
No, because you remember you're not talking about a current there. A wire is a conductor, right?
Well, like if you were to stick a current through the center, would it increase it or would it just
No, no, wouldn't increase it at all. No. No, it's all, the magnetic field inside becomes really, really strong because, for lack of a better term, constructive interference. Okay, let's say that the electric current let's say that the electric current points, the electric current is going, let's say clockwise here. Let's make it clockwise, a little bit easier, okay? Electric current is going clockwise. Let's just erase this. So the electric current is going clockwise. Let's do the Wiregrass Rule, okay? The first rule that we learned, the Wiregrass Rule. Okay, right above the wire, if the current is going clockwise, then, so we've got our loop here, and we said the electric current is going clockwise. Let's stick our thumb clockwise. Okay, we're doing the Wiregrass Rule now. Okay, it's not the coil rule, we're doing the Wiregrass Rule. Let's stick our thumb clockwise. Okay, now let's see where my fingers point outside the coil. They point away from you guys, right? So the magnetic field above that coil is away from you guys, right? Let's take a look at below the coil. If it's going clockwise, then below the coil, I'm going to stick my thumb this way. My fingers would point, again, away from you guys, outside the coil. Agree? Now let's look at both of those places inside the coil. Again, here's my thumb pointing clockwise. That's the direction of the current. Now, if I could stick my fingers inside the coil right now, which I can, I guess, at this end, then which way are they pointing? Towards you guys. Now let's do it below here. Okay, thumb, direction of the current. Inside the coil, which way are they pointing? Towards you guys. So I just did the hand rule in two places, the Wiregrass Rule in two places. I did it above the wire and did it below the wire. Above the wire, I got into the board, or away from you guys, outside, and I got towards you guys, inside the coil. Below the wire, I got towards the board, or away from you guys, below the wire, but inside the wire, or inside the coil of wire, I got towards you guys. Right? Notice that in both cases, inside the coil, my fingers pointed towards you. So that was two fields, two magnetic fields that were pointing towards you. The field caused by the current up here, and the field caused by the current down there. That makes a field that's twice as strong. Does that make sense? Now, outside of the coil, I got a field that pointed away from you, and I got another field that pointed away from you. But one of the fields was up here, and one of the fields was down here. So there's nothing to add up there. Right? I've got a field up here that points away from you. I've got a field down here that points away from you. But inside, I've got two fields that point towards you. What's going to be stronger? Two fields that add together and point towards you, or one field that points away from me, or one other field that points away from you. Not exactly contained, but anywhere you go on that loop, okay, anywhere you stick your thumb and your fingers on that loop, inside the coil, my fingers will point in the same direction. They will outside as well, but they add together on the inside, right? Anywhere I go, my fingers are going to be pointing towards you guys. So a current right here causes a field inside this way. A field right here, or current right here, causes a field inside this way, and so on and so on and so on. Because those fields are all in the same place inside the coil, right, all in that one concentrated area, then we've got a really strong magnetic field. They all add up to give me a strong magnetic field. But outside the coil, they're all going away from you, but one of them's away from you right here, one of them's away from you right here, one of them's away from you right here. They're all in different places. So they don't add up to give me a stronger field because they're all in different places. Inside, they're all in the same place. They add up constructively. Okay. Outside, they don't add up because they're all in different places. Does that kind of make sense now? Kind of? Hopefully it makes a little bit of sense to you. Good question. Question 16. Yesterday, we went a little step further and took a look at what happens when a charged particle moves through a magnetic field that was already there. We know that a charged particle moving generates its own magnetic field. Now, a charged particle at rest doesn't, right? Difference between a charged particle at rest and a charged particle that's moving? Well, they both generate a gravitational field. They both generate an electric field, but only the one that's moving generates a magnetic field. Charged particle moving generates its own magnetic field, but if it experiences another magnetic field that was already there, maybe it's caused by some external magnets, or maybe it's caused by the Earth, or maybe it's caused by some electromagnet over there, those two magnetic fields will interact, the one that was caused by the moving charge and the one that was already there. For instance, Here's two magnets. They generate a magnetic field. And that magnetic field will be from north to south. Let's say we've got a charged particle. Let's make it a positively charged particle. It's moving to the right through the magnetic field. You've got a magnetic field that's there no matter what, whether there's a charged particle or not. We're going to call that our external magnetic field, the one that's labeled in green here. Okay, it's already there. Now we're going to have a new magnetic field that's generated by the moving charge, the red one. That magnetic field will be circular, and we could find its direction by the Wiregrass Rule, but we don't need to find its direction. What we want to find at this point is the interaction between those two fields. The new one that was just made by the moving charge and the one that was already there, the green one, the one that we're calling the external field. There is an interaction which will cause a force. That force will be perpendicular to both the way the particle is moving and the direction of the field. So, if the field is on the y-axis and the charged particle is moving on the x-axis, then the force is going to be on the, got to be the z-axis, right? We always have x, y, and z here. If one is on x and one is on y, the third one's got to be on z. If one is on x and one of them is on z, the third one's got to be on the y-axis. Now, how do we figure out exactly where it's going, exactly what the direction of that force interaction is? For this, we're going to use the hand rule for deflection. This one says, the same as the Wiregrass Rule, stick your thumb in the direction of the particle. So that's what we're going to do. Particle's going to the right. Let's stick our thumb to the right. Left hand or right hand here? Right hand. It's a positive particle, so write that down as soon as you see the question. Right hand. Thumb in the direction of the particle. Fingers are going to point in the direction of the external magnetic field, the green one, the one that points downward here. So thumb to the right, fingers downwards towards the bottom of the page. Which way does my palm point? Into the page. So that's on the z-axis. Okay, we knew the answer either had to be into the page or out of the page when we even started this question. But which way was it? Okay, it could have been either one until we did the hand rule. It turns out with the hand rule that it had to be into the page. So the force is into the page. Let's try another one right now. Let's say we've got a charged particle that's going towards the back of the room. A negatively charged particle that's going towards the back of the room. Let's say we've got a magnetic field that's pointing towards the right side of the room. Left thumb towards the back, fingers towards the right. Which way is the force? Down, towards the floor. Right? Now let's try one more. We've got an alpha particle going towards the right side of the room. Okay, we've got a magnetic field that's pointing towards the ceiling. Which way is the magnetic force? Right thumb towards the right side of the room, fingers toward the ceiling, palm points towards the back of the room. Make sense? Okay. Wiregrass rule, coil rule, hand rule for deflection. 3 rules now. They're all kind of similar, but they're all a little bit different. So we've got to be careful to keep those ones straight. Now, we can also calculate the value of that force. I learned a new equation yesterday. It said F is equal to QV B. Beside the V, you saw a little upside down T. What did that mean again? Not parallel, perpendicular. Means the particle has to be moving perpendicular to the magnetic field. It is in this case, right? We've got a particle going to the right. We've got a magnetic field that's going down. Those are right angles. That hand rule and this equation only work if they're perpendicular to each other. If V and B are perpendicular to each other. If they're perpendicular, we will use that equation every time to find the value of the force. If they're parallel, in other words, if the charged particle is going this way and the field is this way, or if the charged particle is going this way and the field is this way, what's the value of the force then? 0. There's no equation to use there. What hand rule do we use? Why would we do a hand rule if the force is 0? Okay, if you get a charge that's moving parallel to the field, just be grateful. It's an easy question. There is no force. There's no magnitude. There's no direction. Just write down 0 and move on to the next question. If they're perpendicular, get the force by that equation. Get the direction by the hand rule for deflection, and then you're done. If it's something other than 0 or 90 degrees, You don't know how to do it. So good luck. No, you won't have to know how to do it. That's not a part of Physics 30. It's not hard. It's quite easy, actually. But it's not a part of Physics 30, so I'm not going to show you how to do that. Okay? Is that? Effectively, that's what you do, yes. But there is kind of a slightly different version of the equation that takes that into account for you. But that is basically what you do, yes. Good question. What units do you use for force? Well, for force, it's always going to be newtons, right? For charge, it's always going to be coulombs. For speed, it's going to be meters per second. And for B, it's going to be Tesla, right? Yeah, 1 Newton down, or 1 Newton toward the bottom of the page, or 4 newtons towards the left side of the page, or 4 newtons to the south, or whatever the frame of reference is for the direction. Yeah. All right, you had a couple of other questions, or sorry, one other question. It was technically homework, I guess, but you guys all had a chance to finish that up in class yesterday, I think. Any issues with question number 1 on 599? Somebody asked me yesterday, I can't remember if it was this class, how do you find the direction of this question, number 1? Can we? We can't, right? We can't find the direction of it because we're told that the charge is moving perpendicular to the magnetic field. We know the equation applies. We know the hand rule applies. But because we don't know the actual direction, just that they're perpendicular, we can't start sticking our thumb in a direction that we don't know is there. So we can only find the magnitude, and thankfully that's all they're asking for there is the magnitude. Okay? Let's try another example, okay? A carbon ion with a mass of 2.01 times 10 to the minus, I think that's a 26. I think that's a 26. Somebody has their textbook handy and check page 600, that'd be great. See if that's a 26. And a positive charge of 1.6 times 10 to the minus 19 coulombs enters a magnetic field of this value. Find the perpendicular speed. In other words, again, they're telling us it's perpendicular. The equation applies. The hand rule applies. The perpendicular speed at which the magnetic deflecting force will balance the gravitational force. That's a big word, balance. What does that tell us when a force balances another force? There's no net force, and therefore, if we have two forces, they have to be equal to each other, equal in magnitude at least. We've got a mass here, we've got a charge, we've got a magnetic field. Okay, we also have, what are we trying to find here? The speed. Well, if we're trying to balance the gravitational force with the magnetic force, we're going to say Fm is equal to Fg. We're going to say QVB is equal to m times g. We're looking for V, so it becomes V is equal to mg over QB. We get 2.01 times 10 to the minus, did anybody look that up? 1025, okay, thank you. Times 9.81. We're just going to make it positive because we're dealing with magnitudes here, right? Charge is 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. I got 2.10, 2.11. Is that right? I would think there should be an exponent there. Something's wrong with that. No, maybe it's right. It's right. Anybody else get 2.11? Sorry? What'd you get? 0.19? Oh, I see what I did right here. So I'm going to trust you on that because I see that I have made a mistake. So I'm going to trust that you're the right answer. What is it? Say it again. Which is 0.195. Good. You didn't get that? Okay, let's pull out the calculator here and do it together, okay? Yeah, it's 9.81, yeah. So let's use some brackets here. 2.01 times 10 to the negative 25 times 9.81. Let's use some brackets there again. Divided by start bracket again. 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. And we get 0.195. Yeah. It's a pretty slow speed. I would have predicted a lot greater speed than that, but that's what it is. Whenever you see the word balance, whenever you see the word suspend, whenever you see the word hover, anything like that, always just think, okay, which two forces do I have to set equal to each other? Because that's what you're going to do every time. Suspend, balance, hover. Set two forces equal. You just got to find the two relevant forces that you're going to have to set equal to each other. A couple questions here. Guys, we're just going to have you do question 1 and 2A, however, not 2B. We'll take a look at, we won't take a look at 2B later on, but we'll take a look at something that's real similar to 2B later on after we're finished going over these questions. It's about 9:55. I think I'm going to leave it there. I'm going to leave you with, for the next 10 minutes, to work on the questions 1 and 2A on page 600. In addition, though, while you're working on that for the next 10 minutes, I'd like you to take a look at worksheet number 11, please. So practice problem 1 and 2A plus worksheet number 11.